Hello everyone, this is Dr. E, and for today we're going to be learning how to describe the solutions of our linear system. We have several ways on how we can find the solutions of our linear system. We can use the elimination method, substitution method, graphing method, and we can even translate our system into its matrix form to be able to find the point of intersection of our linear system. And for today, we're going to be focusing on how we will describe the solution of our linear system, knowing that we're able to find its solution by graphing or any method that we know how to use. So in this case, the system of linear equations, by definition, it consists of two or more linear equations similar to what we are seeing on the screen right now. And the solution is basically the point of intersection of the lines that we are graphing in our xy plane. So how are we going to use our solution and describe it according to the type of systems we are working on? We're going to start with verifying if the solution of our linear system is indeed the solution given our linear system. So here we're going to determine whether the ordered pair -3 and 1 is a solution of the system x minus y is equal to -4 and 2x plus 10y is equal to 4. So in this case, we're not going to be solving for the solution because we already know the solution. All we need to do is to verify if this is indeed the solution of the linear system. And to be able to do that, we need to understand that the solution given by -3 and 1, which is our ordered pair, should match our first equation and the second equation, and they should have a true statement if we substitute the value of x and y for each one of them. So let's start with the first line. So we know that this is true, or the solution is true for the first line. Now let's verify it on the second line. So knowing that both of them are a true statement for the solution -3 and 1, therefore, we can say that indeed -3 and 1 is the solution of our linear system because we're able to verify it on the first equation and on the second equation, both of which are returning two true statements. So since -3 and 1 makes both equations true, it is a solution of the system, or -3 and 1 is indeed a solution of the system. So let's try the second example. We have 4, 2 as our solution, and we have a new set of linear system. So just like what we did on the first example, we're going to substitute the value of x and y, which is 4 and 2, to the first equation and see if we're going to have a true statement after substituting it. And indeed, -2 is equal to -2 when we substitute x and y. So let's verify it for the second equation this time using the substitution method. So we have 4 and 2 as our solution. This is x and this is y. And the second equation is 3x plus 4y equals 4. 3 times 4, 4 times 2. This is 12. This is 8. This is 20, and it's not equal to 4. So that means this is a false statement. And when that happens, we know that 4 and 2 is not a solution of the linear system because we need to have both lines to have a consistent answer for us to verify if the given ordered pair is indeed a solution or the point of intersection of line 1 and line 2. Now that we're able to verify or learn how to verify our solution, let's use graphing to estimate Keyword is estimate. If the solutions of our systems of linear equation will be found in the point of intersection of lines that we're going to be graphing. So when we are graphing, this is one method that is giving us the estimated value of the solution or the point of intersection of our line 1. So if I say, or systems of linear equation, so if we have 2x minus y is equal to 6 and x plus 3y is equal to 10, so if we are going to graph it by hand, we need to first change our general equations into its slope-intercept form. So what is the slope-intercept form? The slope-intercept form is y equals mx plus b, where this is our slope and this is our y-intercept. And the first line, we have 2x minus y is equal to 6. And the second line is x plus 3y is equal to 10. So if we're going to convert this into an equation that we can easily graph, we isolate the y by subtracting 2x on both sides. And since y is negative, we will switch all the signs of our term so that we'll have y equals 2x minus 6. So this is now our converted line 1 from general equation to its slope-intercept form, 2x minus 6, 2x minus 6. So this is correct. So let's verify, or let's modify the second line. Divide. So this is now our second line, our converted general equation to its standard form. Now the y-intercept is 10 over 3, and 10 over 3 is how many times 3 goes to 10? 3 goes to 10 three times, so it's 3 point something. And we are just estimating, and we don't have a calculator to convert 10 over 3, and we don't want to use the long division to do that, so we're just going to use this estimated value for the second y-intercept, which is at 3 point something. Now, let's use our graphing paper and graph our equation and see if we will hit the actual graph that we are looking for. And to do that, we will need our graphing paper to make it a little bit more accurate and our straight edge to draw the graph of our solution. So you need to remember how to graph your linear equation of this form, y equals mx plus b. And to do that, we need our xy plane. And we're going to be using the grid. So we have the first line at 2x minus 6. So minus 6 is down 6. 1, 2, 3, 4, 5, 6. So this is our first point. And the slope is at positive 2 over 1. So up 2, 1, 2, and then 1 across. So this is now our estimated line using our grid, and let's see how well we're going to estimate our equation using our graphing method. So this is line 1, and line 2 is at 10 over 3, which is 3 point something. 1, 2, 3 point something. So let's put it up right here. And the slope is 1/3 or negative 1 over 3. So negative 1, 1, 1, 2, 3. So this is our second point. And since we are just estimating by our graph and our straight edge, we are not really sure if we're going to be hitting the correct solution for this equation. And the solution for line 1 and line 2 is the point of intersection, and the point of intersection is at 1, 2, 3, 4, 5, and 1, 2 points. So about 2, 1, 2. So this is my estimated solution, and let's see if this is the actual solution for this linear system. So if we use a graphing calculator or if we use Desmos, it will give us a better or a more accurate solution using the graphing method. And in this case, the point of intersection is in the middle, so the graph may look the same. So if we put it this way, you are seeing that it's slightly the same, but with the point of intersection of 5, 2 in my graph, and in the actual graph, it's supposed to be 4 over 2. So since we are estimating, we know that there is a chance that we're going to not hit the actual solution of our system. So in this case, what we can do is just describe that our solution is 1 because there's only one intersection for line 1 and line 2, and that's the only fact that we can generate from our handwritten graph from our solution. But in this case, 4 and 2 is the verified solution of our equation, because if we substitute it to our original system, both of them will give you a true statement. So indeed, 4 and 2 is the solution, and we only have 1 for this particular case. So this is how we use graphing method and the importance of describing our solution using this technique. So let's say I have negative x plus 3y is equal to 6 and 3x minus 9y is equal to 9. If we're going to convert this into the slope-intercept form, the first line will be equal to 1/3 x plus 2, and the second line is going to be at 1/3 x minus 1. And if we're going to be graphing this, let's see if we can graph this. And let's see if we can accurately produce the graph that we are looking for. So we're going to be using the XY plane, and let's see how our graph will transpire. So this one should be quick because both the y-intercept are whole number. With the slope, it's okay if it's in fraction form. Actually, it's better if it's in fraction form, so we can easily graph the slope. Let's graph the first line at 2, 1, 2. So this is our first point, and it says 1/3. So positive 1, up 1, and then 3 across. 1, 2, 3. So this is our second line, our second point, and we will connect the dot of our line 1 and line 2, and let's see if we'll be able to graph it more accurately this time. So 1 or negative 1 is the y-intercept on the second one. And then 1/3 up 1. And then 3 across. 1, 2, 3. We always move to the right, never to the left. The only changing behavior is going up or going down. And this is my graph right here. And this is my graph using my graphing paper, my straight edge, and my marker. Now let's see if I was able to accurately graph my solution. And the actual graph of my solution using technology is actually should be looking like so. And we know that this is not looking the same as the graph that you are seeing on the screen, because again, we are just estimating using the graphing method. So for this case, since this is a more accurate representation of our linear system, we can say that they are parallel and there is no solution, because parallel lines will not intersect in this case. So that means it's a possibility that when you have a linear system, you won't have a solution. And this is one of them, because our slopes are the same. So that is an indicator that the system is indeed parallel lines. And when that happens, there's no solution. And another description that we could use is that the equation is said to be inconsistent. So this is how we're going to be using our descriptions for the solution of our linear system. So if it's intersecting, we have one solution. If it's parallel, there's no solution, and they are inconsistent. And let's test it with this line right here. We have x is equal to 3y minus 1 and 2x minus 6y is equal to negative 2. Changing it into its y equals mx b or mx plus b form. First line is 1/3 x plus 1/3. And the second line is 1/3 x plus 1/3. Now, what do you notice about line 1 and line 2? Line 1 is the same as line 2 when we modified our general equation into its slope-intercept form. And when we have an identical lines or similar lines for line 1 and line 2, we are graphing it, and when we graph it, it will just be showing a single graph. And it's showing a single graph because it's basically two graphs that are on top of each other. So that means we are only seeing one line in the process. And when that happens, we can say that the equations are said to be dependent and there is an infinite number of solutions to the system. It's infinite because if we have the same line, so let's say this is our line 1, and the other line, let's use a different colored marker, is on top of each other. So that means the solution, we have many because it's together. So that's why we have infinitely many solutions when we have similar lines in our linear system. So this is how we describe our systems of linear equation. So to summarize it, if we have one point of intersection, we have one solution in our system. And if we have a parallel line, we have no solution. And if we have coincident lines or similar lines or identical lines, we can say that we have infinite number of solutions. And another way of describing it is if there is at least one solution, just like an intersecting line, we can say that the system is considered to be consistent. And if the system defines distinct lines, the equations are independent. So that means they are different lines. So that means we can use this description when describing the solution of our linear system. So without graphing, since we're not good at accurately graphing our equation, although the method that we're using is accurate or correct, there's still a human error factor because we are graphing it on our own. So let's see if we can describe the solutions of our linear system, if it's one solution or consistent system or independent equation. Or if we are seeing a parallel line, we can say that there's no solution, inconsistent system, and independent equation. And if there is an identical line or lines that are on top of each other, it's infinite number of solutions, or it has infinite number of solutions, consistent system, and dependent equations. So these are the descriptions that we can use for the different types of solutions that we're going to be solving in a linear system. So if we have 3x plus y is equal to 1 and 3x plus 2y is equal to 6 without using graph and by using and relying to our algebra skill, let's change this into the slope-intercept form. So we have 3x plus y is equal to 1 and we have 3x plus 2y equal to 6. By isolating y, we'll have minus 3x on both sides. So we have y is equal to negative 3x plus 1. And in this case, we have to subtract 3x on both sides. So we'll have 2y is equal to negative 3x plus 6. Divide all of them by 2. So we have y is equal to negative 3 all over 2x plus 3. So this is our line 1 and this is our line 2. And without graphing it, we know that the slope will determine our solution or how we're going to describe the solution of our system if line 1 is negative 3x plus 1 and line 2 is equal to negative 3 over 2x plus 3, we can say that we have one solution because they're intersecting, and that's the only description that we can say, or the only way that we can describe the solution. There's one solution, and according to its system, it's consistent. So that's how we're going to describe our solution, by modifying our general equation into the slope-intercept form. So if we have 3x plus y is equal to 0 and 2y is equal to negative 6x, if we modify this using algebra, for the first line, we have 3x plus y equals 0. Second line, 2y equals negative 6x. By subtracting 3x on both sides, y is equal to negative 3x. And on this case, by dividing both sides by 2, y is equal to negative 3x. And what you are noticing is that we have similar lines. The slope are the same. The y-intercept are the same. They're both at 0. So that means line 1 and line 2 are equal or the same. So we can say that the two lines are identical. So there are infinitely many solutions for this particular linear system. And if we have 2x plus y is equal to 0 and negative 2x plus 1, changing it in the slope-intercept form, we'll have y is equal to negative 2x, and the other one is going to be y is equal to negative 2x plus 1. And the slopes of line 1 and line 2 are identical or similar, but the y-intercept are not the same. The y-intercept of the first line is at 0, the other one is at 1. So in this case, they are parallel. So that means there's no solutions in our linear system and that the lines are inconsistent. So this is how we describe the solution using our descriptions, by identifying the slope of our equation and converting the general equation into its slope-intercept form. So for our Numberbender challenge of the day, you need to describe the solution of the linear system. Is the linear system has one solution, no solution, two solution? Is the system independent or dependent? Or is it consistent or inconsistent? So let's see if you can answer the description, or you can write the description of our linear system without even solving it by looking at the graph. And that is our lesson for today on solving for the equation or describing the solution of a linear system using the facts that we have established in our lesson today. So this is Dr. E, and see you again next time. Bye!